Welcome back to the HVAC Master Training Series. Today we're diving into psychrometrics, the science that explains how air and moisture interact in every HVAC system. Psychrometrics is the study of the thermodynamic properties of moist air and the processes that change those properties. It's the foundation for understanding air conditioning, dehumidification, humidification, and all HVAC processes involving air moisture. Every HVAC system manipulates air properties. The psychrometric chart is your roadmap showing exactly what happens during heating, cooling, humidification, and dehumidification processes. Let's walk through the key moist air properties you'll find on a psychrometric chart, the foundation of HVAC air analysis. First, we have the dry bulb temperature, often called the DBT. That's just the regular air temperature you measure with a standard thermometer. It's shown along the bottom, horizontal axis of the chart, and it's measured in degrees, Fahrenheit, or Celsius. This is the most common temperature we use when talking about air. Next, the humidity ratio, symbol W or omega. It tells us how much water vapor is in the air compared to dry air, basically the moisture content. You'll find it on the right vertical axis of the chart. It's measured in pounds of water per pound of dry air, or kilograms per kilogram. It stays constant when air is heated or cooled sensibly, but it changes during humidification or dehumidification. Now let's talk about relative humidity, or RH. This one is familiar. It's the percentage that tells us how humid the air feels. It compares how much moisture the air has to how much it can hold before reaching saturation. You'll see these as curved lines on the chart, 10%, 20%, 30%, all the way up to 100%. When you hit 100%, that's the saturation line, the far left edge of the chart. Moving on, the wet bulb temperature, or WBT. This is measured with a wet cloth wrapped around the thermometer bulb. It's a mix of temperature and humidity effects. On the chart, wet bulb lines run almost parallel to the enthalpy lines. The wet bulb is always equal to or lower than the dry bulb temperature, and they're equal when the air is fully saturated. Wet bulb readings are super important for cooling towers and evaporative cooling systems. Next up, the dew point temperature, or DPT. This is the temperature where air starts to give up moisture, when condensation begins. On the chart, you find it by going straight left to the saturation line. It doesn't change during sensible heating or cooling. In HVAC design, it tells us the cooling coil leaving air temperature, which helps prevent condensation issues. Now let's talk about enthalpy, symbol H. Enthalpy means the total heat content of the air, both sensible and latent heat. The simplified equation in IP units is H equals 0.240 times the dry bulb temperature, plus W times open parenthesis 1061 plus 0.444 times TI close parenthesis, in BTU per pound of dry air. On the chart, enthalpy lines slope diagonally from upper left to lower right. You'll use this property all the time in energy and load calculations. Finally, the specific volume, symbol V. That's the amount of space 1 pound of dry air takes up. At 70 degrees Fahrenheit and sea level, it's about 13.33 cubic feet per pound. Specific volume lines slope upward from the lower left to the upper right. It's used when converting CFM to mass flow rate, and it varies slightly with altitude and temperature. Together, these 7 properties give you a complete picture of moist air behavior, helping you design, analyze, and optimize HVAC systems with confidence. Air is a mixture of dry air plus water vapor. Each component follows the ideal gas law, and together they obey Dalton's law of partial pressures, meaning the total pressure equals the sum of the dry air pressure and the vapor pressure. At sea level, that's about 14.7 pounds per square inch, or 101 kilopascals. Let's go over the fundamental air processes shown on the psychrometric chart, the key to understanding how air behaves in heating and cooling systems. On the chart, each type of process moves in a certain direction. Sensible heating moves horizontally to the right. Temperature rises, moisture stays the same. Sensible cooling moves horizontally to the left. Temperature drops, moisture stays the same. Humidification moves straight up. Air gains moisture. Cooling and dehumidifying moves down and to the left. Both temperature and moisture drop together. Now let's break them down one by one. Sensible heating happens when we add heat to the air without changing the moisture in it. On the chart, that's a horizontal line moving to the right. Here's what's happening. The dry bulb temperature goes up. The wet bulb temperature also goes up. Relative humidity drops, and the dew point stays the same. The humidity ratio, or moisture level, doesn't change. The formula for sensible heat is simple. Q equals 1.08 times CFM times delta T. That's in IP units. Or in metric, it's 1.20 times liters per second times delta T. You'll see this process in electric heaters, hot water coils, gas furnaces without humidifiers, and steam coils. Now let's flip it around. Sensible cooling is when we remove heat from the air, but moisture stays the same. On the chart, that's a horizontal line moving to the left. Here's what changes. Dry bulb temperature goes down, wet bulb temperature goes down, and relative humidity goes up. But again, humidity ratio and dew point stay constant. Here's something important to remember. Sensible cooling only happens if the cooling coil temperature is above the air's dew point. If the coil gets colder than the dew point, water starts to condense, and that means dehumidification begins. You'll see this kind of cooling in chilled water coils that stay above dew point, heat recovery systems, and indirect evaporative cooling setups. Humidification process moves vertically upward in the psychrometric chart. Moisture is added on the air. Dehumidification process moves vertically downward in the psychrometric chart. Moisture is removed from the air. Cooling and dehumidification. This one is a mix of both. We're cooling the air and also removing moisture. It happens when the air is cooled below its dew point, so condensation forms. On the chart, that's a line moving downward and to the left, toward the saturation curve. During this process, dry bulb temperature drops, humidity ratio drops, and enthalpy, or total heat energy, also drops. That means we're removing both sensible heat and latent heat. This is exactly what happens in an air conditioner or a cooling coil when you see water dripping. That's dehumidification in action. Heating and humidification. When both temperature and humidity need to increase, the process is called heating and humidification. You'll see a line rising upward and to the right on the psychrometric chart. This happens in winter when air is cold and dry, and we use steam humidifiers, ultrasonic humidifiers, or evaporative media to add moisture. The air gains sensible heat from the heater and latent heat from the moisture added. In comfort applications, we typically raise relative humidity to around 40–50% to prevent dryness and maintain good indoor air quality. Evaporative cooling, adiabatic process. Next is one of the most energy-efficient natural cooling methods, evaporative cooling, also known as an adiabatic process. Here, water evaporates into the air, which increases humidity while lowering temperature. No external heat is added or removed. The total heat, or enthalpy, stays constant. On the psychrometric chart, this process follows a diagonal line that roughly parallels the constant enthalpy line, sloping downward to the right. You'll see this in cooling towers, evaporative coolers, and even direct-indirect evaporative systems designed for hot, dry climates. It's an effective low-energy method for pre-cooling ventilation air before mechanical cooling takes over. Chemical dehumidification, desiccant process. Finally, we have chemical dehumidification. In this process, air passes through a desiccant material, such as silica gel or lithium chloride, which absorbs moisture from the air. As moisture is removed, the air's humidity ratio drops, but the desiccant releases heat, so the air temperature rises. On the chart, this process appears as a line moving downward and slightly to the right, drier but warmer air. Desiccant systems are used in industrial drying, ice rinks, museums, and any application requiring low humidity levels beyond what cooling coils can achieve. When outdoor air mixes with return air, the mixed condition lands somewhere on a straight line between the 2 points. For example, if 25% outdoor air at 95 degrees mixes with 75% return air at 80 degrees, the mixed air will be close to 84 degrees. To understand the heat balance, we use something called the sensible heat ratio, or SHR. It's the ratio of sensible heat to total heat. We say it like this: SHR equals sensible heat divided by the sum of sensible heat plus latent heat. If the ratio is 0.8, that means 80% of the heat is sensible and 20% is latent. SHR lines on the chart help us visualize how the air is cooled or heated. Next, we use the chart to calculate how much supply air we need. The formula is simple. CFM equals sensible heat divided by 1.0085 times the temperature difference between the room and supply air. For example, with an 80,000 BTU per hour sensible load and a 75 to 56.5 degrees F temperature difference, the required airflow is about 3,430 CFM. The psychrometric chart also helps find coil leaving conditions, supply temperatures, and airflow required for comfort. Now, let's talk about total cooling load. We calculate it using enthalpy, which measures total heat energy, both sensible and latent, in 1 pound of air. The formula sounds like this. Cooling load in BTU per hour equals 4.5 times the airflow in CFM times the difference between entering enthalpy and leaving enthalpy. For example, if airflow is 3,430 CFM and the enthalpy drop across the coil is 9.2 BTU per pound, then cooling load equals 4.5 times 3,430 times 9.2, which gives you about 142,000 BTU per hour, or roughly 11.8 tons of refrigeration. Remember, 1 ton of cooling equals 12,000 BTU per hour. At part load conditions, the sensible heat ratio drops because latent load stays steady, while sensible load decreases. Constant volume systems that vary temperature can lose humidity control. That's why reheat systems or bypass coils are used to maintain proper indoor relative humidity. These methods use more energy, but they help maintain comfort across changing conditions. Practical HVAC applications of psychrometric charts. Determine entering, leaving coil conditions. Balance sensible and latent loads. Select proper supply air temperature and airflow. Evaluate coil capacity and system behavior under variable load. Essential for design of AHUs, DOS, and control sequences. So to wrap it up, the psychrometric chart is not just a diagram. It's the foundation of HVAC system design. It helps engineers balance temperature, humidity, and airflow to create comfort efficiently. Mastering psychrometry means mastering the language of air conditioning. If you found this helpful, don't forget to subscribe to HVAC Master Training for more deep dive sessions on HVAC design and system analysis.